Okay, next problem, 5.7. Sorry, that's not right. 15.7. We are told two uncharged spheres are separated by 2 meters. This is 2 meters. These are neutral, uncharged. That's what it says, uncharged. Then we take 3.5 times 10 to the 12 electrons from this one, and we place it on this one. So this one loses this amount of charge, and this one gains this amount of charge. And now we're asked to determine the electric force between them. Okay, well, the electric force is K, Q1, Q2 over R squared, the distance squared, right? And in this case, it's going to be 8.9 times 10, excuse me, was it to the 9, 10 to the 9? I would double check that if you're going to do that in the calculation. Right, newtons meter squared, charge squared, times 1 over 2 meters squared times the charges. So now, like I said, this one lost this much charge and this one gained this much charge. So that means we have 3.5 times 10. Let's go here. Let me double check this. To the 12 squared. One of these was negative, so it actually should be, depending on how you define your vector space. If this is positive x, then it'd be going this way. Or no, sorry, the force would be going this way for positive x over here. Okay, so that would give you this value, so you can plug that into a calculator. That's not that difficult to do. Let's move on to the next problem. Okay, we have a setup here, a y-axis, a 5 nanocoulomb charge. This is 0.3 meters long. This is a 6 nanocoulomb charge. This is a negative 3 nanocoulomb charge. This is 0.1 meters. So this distance is 0.1 meters. This is 0.3 meters. Okay, we are asked to find the magnitude and direction of the force, of the electric force between... Oops, I didn't write this here. This is a charge down here. So we have 3 charges. That's what I'm trying to say. 1, 2, 3. We want to find the electric force between all of them. So just at a glance, we have 2 charges, right? 2 positive charges this way. This one is stronger. This one is stronger than this one over here. We're likely going to have a force going in this direction. And then this one is negative. This one's positive. We're going to have a force going in this direction. So before we actually do the calculation, we're going to have something. It should probably look like that. This should be the force should look something like that. Okay. So let's figure out the first force. So we have a 5 nanocoulomb and a 6 nanocoulomb charge. So we have F5, 6, but we could let's call this F6 to make it easier. So F6, then the first force between this one and this one, we have K, our K value that we've written down a few times. It's 0.3 meters. This is all squared. This is our distance squared, right? We have our first charge, coulombs, 5 nanocoulomb is 10 to the negative 9. Right? So here we have coulomb times coulomb, that's coulomb squared, meter squared. Those units go away. We're left with newtons, and this gives us a value of 3 times 10 to the negative 6 newtons. Okay, let's do the next one. We had one that was 5 nanocoulombs and negative 3 nanocoulombs. We'll just call this one F3. So for F3, we had a negative charge. Let's put that out front right away. We had 5 nanocoulombs. We had negative 3. Oops, I already wrote that down. Right? Yeah, 3, okay. And then it was 0.1 meters. We also should note that this force is going in the negative y-hat direction. So, recall this one was positive x-hat. And this one will be going in the negative y-hat direction. Let's see. There we go. That's what I meant to do. Okay, anyway, plugging these values in for F3, we end up getting 1.35 e to the negative 5 newtons. Okay, so now we want to find the magnitude between all of this. So F total magnitude. We can take our two forces. Remember that we have r is equal to x squared plus y squared, all under square root. This is magnitude of r. So magnitude of F then is going to be F3 squared plus F6 squared, all under square root. This is going to give us approximately 1.38 times 10 to the negative 5 newtons. Okay? So we had two forces, one going in the x direction and one going in the y direction, so we called this x and this y our components of our total vector. So recall that y over x is equal to tangent theta. Now if we want to find the direction, we take tangent, the arctangent of y over x is equal to theta. So which one was y? It was F3, right? Going down here, F3 was our y. So, tangent inverse of 1.35 times 10 to the negative 5 newtons over 3 times 10 to the negative 6 newtons. This gives you, in degrees, it's about 77.47 degrees. That's what I ended up with. The method is there, so if there's a discrepancy with this, I would double check this. It would be to do with calculator being in radians as opposed to degrees, which is pretty common. Okay, next problem. I'll post the next one as its own video, because it's kind of a long one.